Já pode compartilhar, Vander, se quiser.
Chegou aí?
Okay, welcome back. We have the pleasure to have Professor Vander Alves, as a keynote speaker for this session. Just a brief introduction. Professor Vander is an associate professor at the Computer Science Department of the University of Brasilia, Brazil. He was a recipient of the Alexander von Humboldt Experience Research Fellow, made at the University of Passau, Germany. His research interests include software product line engineering, which is the main topic of his keynote talk, body sensor networks, and formal methods. He has numerous impactful publications in the most prestigious conference and journals, which is made him a very renowned researcher in his area. He's also a dear friend, so it's a pleasure to present Vander's keynote talk today at the SBMF this year. Thanks, Vander, for accepting the invitation.
Thank you very much, Thiago, for the introduction. Thank you very much, Sergio, for the invitation. So the talk is on software product line analysis, reliability, and beyond. So I would like to acknowledge a number of research partners that have substantially contributed to the research that I'll talk about today. When we consider different areas of application that somehow affect our lives to some extent, we can identify among different concerns two very important ones. So these systems, they tend to have a lot of variability. So variability in the way that, so what's the property that the system can be adapted to different scenarios, and the reliability. So by reliability, we mean the probability of reaching a success state. So the talk will be on how to relate these two concerns, and we'll do that by motivating in a concrete scenario, right? And then later, towards the end of the talk, we'll talk more about how these ideas could be applied to different properties other than reliability. So the scenario that we're considering is the body sensor network. So this came about with interaction in with a university hospital. We have a collaboration there with some colleagues, and the idea was that we developed a system that efficient that could be running and the mobile phone, for instance, of a patient, and these. And this system, so the person is wearing a number of sensors. These sensors are collecting vital signs from the person, These signs are analyzed to identify some situation of interest, and depending on what happens, then the system can react in a way so that it can change some, it can activate more sensors or deactivate other ones, or change the sampling rate of the current sensors that are activated. So this system has different kind of variabilities, and is a system that has also important concern regarding reliability. Okay, so for instance, I mean, the idea of the system that, okay, it captures vital signs, then it identifies some situation of interest, it computes some quality goal, and if necessary, changes the configuration. So normally these activities here are related to detailed with some other behavioral models, such as, for instance, sequence diagram that shows the interaction between the different components. For here, for instance, to collect the oxygenation information, it shows how these components interact. And we have some annotations here showing some optional fragments that are related to functionality that the system may have or may not have, right? In terms of reliability, at a very high level of specification for this system, a domain model of quality regarding reliability was developed with a domain expert, in this case, a medical doctor. And basically, according to his knowledge and to the body of knowledge in this domain, the system can have three reliability states, and it will change over time from one state to another, depending on the occurrence of certain events. So, for instance, the person's okay, but then there is some low oxygen event that is detected by the sensors. Then the person, the state of the system will move to high risk reliability goal, and the system somehow has to react to that, right? So that's the idea of such applications, right? Later I will detail more the reliability analysis and more on the variability, just to have an idea of what kind of architecture and deployment we could have here. So basically, on the left here, we have components that are running on the mobile phone of the patient. The blue components here form a kind of closed loop. So the monitor, analysis, planning, execution, knowledge, architecture style, whereby information from the sensors are collected and it's interpreted. It's compared to the planning. So the planning uses some kind of state machine, basically which is running the reliability goals. And if there's some transitions there, then the system has to synthesize a new configuration, and this continues. So the green element here means that, and this part here is running, for instance, in the environment of the medical doctor. For instance, the medical doctor can edit, compile a given reliability goal or state machine, and then this is sent to the, and then that's sent to the patient, right, over the air. And this is on green because this can change also over time. So this machine can also change over time. And the motivation for that is that, for instance, if we're using that for doing some physical exercise as time continues, then we can adapt, we can be more fit, so we can change that. And also medical knowledge itself evolves. So what is considered, for instance, low pressure, high pressure, and so on. These boundaries, they keep changing from time to time, right, according to the domain knowledge. And so sometimes it's necessary to update this. Okay, so this is to basically to motivate the scenario where we explore variability and reliability. So a bit more about what we consider here in terms of reliability. So we start with some model, basically probabilistic model, so discrete time Markov chains, which which we do some model checking to compute the reliability. So, okay, we have a probabilistic model here, right? And we do the model checking basically. So we want to know what's the probability of reaching the success state. So basically, we have to compute the different paths leading to that state, right? So that's what we mean by reliability. In terms of variability, as we said, it's an important concern in a lot of systems. Actually, it's virtually present basically everywhere, right? So we frame this key problem within the product line idea, where we have three basic elements, right? So we have what we call feature model. It's a way to describe the possible configuration of the system. We have some reusable artifacts. That's what we call the asset base, and we have some mapping rules relating the features from this feature model to the artifacts of this asset base. So that's what we call the configuration knowledge. So, okay, so the feature model that we mentioned before, here we're showing the feature model for the body sensor network. Basically, it's a hierarchical way of presenting the features of the system. This model also shows what we can select and what we can not select for a given configuration. So for instance, here, it's always the case that we have monitoring, storage, sensor information, sensor features, but from the sensor information, if we should select at least one of these features, the same for sensor, and for storage, we have these alternative features. We should select only one of them for a given configuration. In addition, we have some constraints here that relate these features, right? So for instance, we select in any configuration where the pulse rate feature is selected, then we have also to select either the SPO or the SEG sensors. And the motivation for that is that either of these sensors provides such kind of information, right? So so basically we're showing here what the semantics of this model is, the set of possible configurations, right? And the system, the body sensor network, at any point in time, it is in a specific configuration that is fulfilling or providing a certain reliability. Okay, so with the product lines, basically we make a selection. The feature models, we select some features that respect the constraints of the model, and together with the configuration knowledge, the mapping rules, we derive a product. We perform what we call product derivation, right? In the same way, make an analogy that when we go to restaurants, we have a menu. The menu is the analog here of the feature model. From the menu, make a selection. That's our order. That's the configuration. And from that, we get a product. So there we have a specific dish for us to enjoy. And here we have some kind of product. This can be a specific Linux distribution. And here we can have the Linux kernel. And here we have all the macros that we use for the kconfig in the Linux system, for example, which is a very clear and pervasive example of variability and software product line. So in our case here, so when we are modeling behavior, it's interesting that then when we are building the asset base, okay, that we indicate variability somehow, and in this case we leverage parametric Markov chain to do that. We show, how we compute that the property of interest. But from this model, we later, when we do the derivation, we can have a specific discrete time Markov chain, right? So that's, but the idea is that, okay, we can focus a lot on this model here, which has a lot of commonality between the possible discrete time Markov chains that we can instantiate. Okay, so where does this model come from, right? Basically, when we start the system, we have, okay, as usual, some kind of informal and sometimes some formal specification, but we depart from behavioral models such as activity and sequence diagrams, which already have some indication or annotations of variability as optional fragments. These, these names here, they refer to features that are within the feature model, right? And they are used for us to perform the construction of the parametric Markov chain on which we're going to do the analysis. We're making some other assumptions. The system outputs a correct result, success or fails. The space is finite, and we're not considering parallelism and non-determinism. So how do we model variability in these models, right? In these probabilistic models. Okay, so basically we want to consider a specific model fragment, and how can we make it optional? There are basically two different approaches. So in the compositional approach, we have a separate base model, which we want to compose into a given slot in the original model. This slot, so basically what we do is we make some transitions here from the extended model to the base model, which are going to be triggered regarding to some selection of some variables. Okay, so it's important that this base model and the dependent model. So there's some induced dependency here, which is respected. In the annotative approach, we use what we call switch transitions, which allow us to bypass the given model that we want to make optional, right? And we can switch from annotative and compositional approaches naturally. So, for instance, based on the selection of the variables, then we can follow the switch transitions or not, right? So in this case, we just follow the base, the element here. So, and in this case here, we just skip the base element, right? Okay, so in the end, we have some probabilistic model with some variability. We have some description in terms of the rules that these annotations, these features have to follow. So they must comply with some rules of the feature model. And we want to analyze this model for the property of features here in terms of reliability. So what's the result? So the type of the result here is not going to be a real number. So it's going to be an expression, right? Because exactly of the variability. So for instance, in this example here, because of the variability, then when we compute, we follow the path to the success state. Then we have this expression. So basically, this is driven by the configurations that we can have from the feature model, which will have a correspondence to the selection of these variables in the model. And as a result, we will have, for different configurations, we have different reliability values, right? But this is more like semantically, or we could compute this way. I mean, actually, we'll talk about some approaches that do that. Okay, so there we can represent that a bit more in a compact way. So, for instance, in one approach that we use, we leverage algebraic precision diagrams. So ADDs allow us to make a more compact representation of the results, right? So, for instance, and these, so the arguments here, they correspond to features, and they are shown here as presence conditions, which will correspond to sets of configurations that will have a specific reliability value. So we synthesize that and avoid doing the enumeration. So for instance, here we have two ADD, right? ADDX, ADDY. Here we're just listing, enumerating the values, right? And then when we do the multiplication, here's the result, right? So there is a algebra library for performing these operations. That's what we use to just avoid doing enumeration of the results, right? Because then in a product line, normally, so in the worst case, so the number of configuration grows exponentially. So that's very rapidly we can have not manageable number of configurations to do some to do any kind of analysis on top of the expensive analysis themselves that exist already for single systems, right? So okay, so one approach that we talked about here, so was published in the group some years ago. So it's the feature family-based reliability analysis. So the feature-based, the feature dimension here means that basically we're doing some compositional model checking, some composition analysis. The family dimension refers to the idea that we have some parametric models, right? So we have some annotations here that refers to the features. And the idea is that instead of taking this big model here and deriving a concrete BTMC, discrete time Markov chain from this model, and analyzing each one separately, basically we try to explore as much as possible the common parts. So for instance, this part here is going to be common to all the possible instances, right? So at some point, of course, we have the branch, the variability, but that we try to handle as efficiently as possible. So the question is still, okay, what's the reliability of this system? And in this approach, we perform, we first do a decomposition of the models, exploring, identifying the, with their dependencies, right? So there's a dependency between these models. And for each of them, we do the parametric analysis. At first, so we use we can use a model checker like Prism or Param, right? That will provide us here and in each submodel an expression. And then, okay, to avoid the enumeration, when doing the step back here, we use switch these expressions to ADD algebra, and then do all the computation here using ADD algebra until eventually we arrive at a larger ADD, which has the reliability of the whole product line. So for instance, if both features F and G are selected, this is the reliability, right? So this is one approach to do that, and we compare this approach to different approaches, right? So that's the feature family. We compare to feature product family product, and there are different ones. I'm going to talk a little bit about how other approaches can be built, considering for performing this analysis. So so in terms of time and space, okay, it eventually explodes, right? But we delayed the explosion a bit, right? So that's what we observe for this body sensor network product line, and for some other product lines that are larger, have about 100 features and so on, right? So this is some empirical results that we arrived. There are some possible extensions and possibilities for future work that we're going to discuss later. But also, then a question arose, and of course, from the conceptual and theoretical point of view, right? I mean, what are these other approaches here, right? And the fundamental question is, do they all yield the same result? So what's the soundness aspect here, right? So we can take a parametric model, do the parametric analysis, and have some formula, and then evaluate the formula, or we can bind the variability, have a concrete model, and analyze it, right? So there are different ways to do that. So following this research, which started more empirically, we started to follow a more conceptual or theoretical investigation, right? So is it true that different user-oriented reliability analysis strategies yield equivalent results for any given product line. So that became our concern. So as we mentioned, the feature family-based strategy, we depart from a compositional model, do some parametric analysis. Here, just a simplification. So it's a parametric analysis in each of the components of this composed model, right? So it's a F-map. Actually, we're going to talk about this later, but we're doing parametric analysis in each part of the bigger model. Then this will lead to composition expressions, and which will lift each of them to ADG algebra, and then we do compute the reliability. So that's just to represent here what we showed before. We're representing this way because we're going to compare to other approaches, and you can see the shaded areas here, which represent the other approaches, right? So, for instance, another approach is the feature product-based strategy. Just skips this listing here to ADDs and already performs the evaluation, but then we're doing the enumeration, right? But there are some approaches that emerge doing this. Or we can use a more like standard approach, with kind of a baseline. So we take the model, it can be some annotative model, we bind the variability, and then we analyze the model without variability in terms of reliability. Then here we can use just the standard techniques, right? The issue here is that then we have to bind the variability for every configuration and then do the analysis. So this is really very rapidly, this does not become feasible anymore. It's not, it just explodes very quickly, this approach, right? I mean, overall, there are different possibilities, right? To additional possibilities, there are 7 overall. So basically, we either start from the compositional model and from annotative models and follow a path to reliability. Each of these paths represents an analysis strategy of reliability. So the question is, do these all paths yield the same result? So that's the question. So this is, we investigated this. Some years ago at SCP, we performed a manual formalization and a manual proof of this, right? Basically, this is synthesis of the work, but in the end, you see there's some, I mean, there are a lot of some details about this, but this basically summarizes this number of commutative diagrams here within this whole diagram. Basically, it says all these analyses correspond to each other from a conceptual and theoretical point of view. That's important, right? But from a practical point of view, all of these paths, all of these analysis strategies, then they may have different empirical and practical complexities, right? So that's what we showed before. For instance, the feature family-based analysis that seems to be a bit more promising than the other approaches at the moment that we explore this, right? Okay, but then we came to this more theoretical investigation, right? And so this was, as we said, it was manually formalized, right? But later on, right, to increase the confidence in the results, we decided to do a mechanization in PTS. So we revisit the formalization, but now mechanically. So I mean, I just provide here the key ideas and the strategy, right? And I'll provide the link in the report story with the formalization. But so basically, we have in each of these nodes here, right? So we have the models. So basically, these are types, right, or sets of types. That so for instance, the parametric Markov chain is this tuple here, which has this number of elements. Then we use a suitable construct in the specification language of the proof assistant. So here, record types with field elements here. It provides some resources for dependent types and predicate subtypes that was very useful. So for instance, here we have an evaluation function that binds variability, in a parametric Markov chain, given an interpretation of the variables. And this interpretation here must check that this function F here, okay, is well-founded, as well-defined. And this basically we're showing a way here to use not only dependent types, but also predicate subtypes in PZS for doing the analysis. But what's important to say here is that this generates some quite a number of proof obligations, right? So so some of which can be discharged automatically and others have to be proved, right? And the commutative strategies that we mentioned in the diagram. So for instance, they will be defined. So for instance, the baseline one, the product-based analysis, it will just do some composition of functions, right? So first, here we bind the variability, and then we do the analysis. And in the product, and the family product-based analysis, basically we do the parametric analysis, and then we do the evaluation. Here the names are not relevant. I'm just saying what they mean, right? This is just an excerpt of the specification. I'm omitting here also type declarations and so on. But the idea is that for each, then we have a number of theorems for that state the commutativity, right? So for instance, we have a theorem saying that the family product-based analysis yields the same result as the product-based analysis given some model and configuration, right? So for every model and for every configuration, so these analyses they correspond. I mean, this is just a very high-level taste of the specification, right? More details can be found here in this link. So should say that this took about, and it's not completely finished, but it took about two years of a PhD student's work and with some assistance, right? So to have an idea, so the theory has about a bit more than 1,000 theorems and lemma, right? And we can classify them into user-defined, so that we had to specify some proof obligations that were manually dealt with, and some proof obligations that were automatically discharged with the proof assistant. Okay, so this is regarding this theoretical investigation, right? At least the start of it, right? So the benefits that we could that we had in this experience. So we had to correct the original theory, the pen and paper theory in some aspects, basically some missing preconditions, some details like that. So usually the specification involved, you had to verify if everything was consistent again. So running the proofs automatically was important until we could find that there was something that was breaking and we had to address. But that was also challenging to deal with evolution. Actually, it's one of the future work that we'll talk about. And okay, we could, there's some possibility for automation, as we mentioned, but on the other hand, there was also much more specification effort, right? So it's a big endeavor, right, if you want to do that. I'm sure you appreciate that. Okay, but so okay, we had this question here, right? And we had this diagram. Do these analysis strategies all correspond and so on, right? But okay, as we were progressing with that, and I'm also here trying to convey a bit of the experience that we had, right? Not only the results, but also the experience. I think it's important to give an idea of how the research evolved and also for discussion for future work, right? But then at some point we started to ask ourselves, okay, does this is it specific only to reliability? All this, right? I mean, and why did we start to question that? Okay, so we didn't start all this research from scratch. At least informally, there are a number of surveys in product line analysis that classify these analyses in these different dimensions: family, feature, and product base, as we mentioned before. But these were like informal surveys, right? We were not formalization, but we were inspired by this informal work and by our specific interest in reliability. But then we started to think, okay, maybe this is it possible to apply this experience to different models and to different properties? So that became the following question, right? So can we apply this to control flow graph, to UML profiles for security, performance models, probabilistic annotation, activity diagrams, for instance, or some other models, right? So that we could investigate different properties, so for data flow analysis, security, performance, and do model checking of different properties. So this question, right, led us to propose an initial model that generalizes the commutative diagram to different models that we call here just products, and to different properties that we just call property here, right? So this is earlier work this year at CN1000 that gives the details about this. So this was also formalized in PPS. We went directly for the mechanized formalization, but the idea here is okay. So we have a model, we have a property, and we have a composition of this model, and then we do some analysis, and then we can do that also in the compositional side or not, or in the annotative side, right? So we specify these and formalize. So the idea, I mean, the base idea was to use, for instance, in CVS, we started to use just uninterpreted types for product and property. And here, for instance, in this composed product line, we just use some parameterized type structures and build and follow just the dependencies, right? Okay, so this is was the generalization of the previous investigation. Okay, so now we want to highlight here some specific points when we look in this diagram. So there are some abstractions that are of interest that became clear later. So for instance, when we consider from either side, so from the compositional side and to the annotative side, so inward, as we go to the center here, we're doing some kind of variability binding, either in a compositional or in an annotative model. Okay, and this binding can be in product, in the models, or in the partially analyzed artifacts, so composition expressions or listed expressions. So this is one abstraction that became clear. So another one was, so on the left side here, so because we're talking about this compositional model, compositional product line, right? So here there's a component functor, and this component functor is basically, so here that this is a simplification that I'm going to explain now. So if we take this, okay, we look at this side here, but now we replace it in the horizontally. So we start from the compositional model and go to composition expressions, and then to lifted composition expressions, right? So this is this structure here is a functor, right? And from one model to the other, we're doing just a F-map here. First, we do a F-map of the parametric model checking. That is, we apply the parametric model checking in each of these models here, right? And then we have now the same structure, but now the nodes have the formulas, the expression. And then we take the same structure and visit each of these nodes. So that's the F map again, but now doing the lifting to a specific algebra here in the case for doing ADD operation, right? So this is became clear as we developed this generalization, right? So again, this was formalized and mechanized in PTS. Okay, so especially in this general part here, because there are some axioms that we have to assume. For instance, on the compositional side here, there must be some compositional functions that do some kind of composition. I mean, so there's some base facts that we have to state here. There are some unfinished parts of the mechanized proofs, but still it's mostly done, right? There are some assumptions on the Markov chain models that we use. Okay, there was an informal refinement to implementation. We basically did the formal analysis, right? But the implementation was doing just following some agile methods, so to say. And we started from an industrial motivation and a collaboration with industrial partners. But to evaluate this kind of system, we need to continue this collaboration. And also there's some ethical issues involved that we wanted to really to do that in a patient, right? So we have to, I mean, even these days, even for other kinds of research in software engineering, but especially this, since we're dealing with analysis of medical data and so on, right, and personal data. So it's important to continue with that further. So as a future work, I mean, there are a number of possibilities here that could be explored. So as I mentioned, we did the formal specification of the general theory, but we have not done yet a mechanized instantiation of that. So that's one possibility that could be explored. Another possibility that's a pretty hot topic these days is community software engineering in general, but also in the product line community, it's considered model evolution. Why? Well, it happens, right? So it's we cannot avoid that, and it has a cost because I mean most approaches, surprisingly, in most approaches they have to do the analysis from scratch again. They really don't really explore incrementality in the analysis, right? Even though there is the analysis compositional, at least the first time it is done. But as the model evolves, which is 100% sure that this happens, then, but surprisingly, the analysis just ignore that. So this is being explored for other kind of analysis in terms of product line, but in software engineering in general. And we also interested, and we also exploring that even in the context of reliability analysis, right? Okay, there are some ideas. The amount of reuse that we can make in terms of the analysis will depend naturally in terms of the specific analysis, how compositional that analysis is, and also in terms of the base model and how the model evolves. If the model evolves nicely and this is nicely aligned with a compositional analysis, then there could be a lot of opportunity for reuse. But I mean, it always depends on case, but for different systems, for instance, for product lines, we have some patterns of evolution that are more common, right? So the software artifacts, the base artifacts, they tend to evolve much more compared to the feature model and to the configuration knowledge, for instance. So this is really, I think it's very interesting topic that could deserve at least one talk for that, but it's a very active topic. Automation, right? So, I mean, we can think of a generic generic diagram. But in a way, I mean, is it possible in a complementary way? Can we synthesize automatically a variability-aware analysis from a non-variability-aware analysis? Can we do that, for instance, using metaprogramming or and so on, in a complementary way to having a generic taking a generic approach, right? So because this, when we have kind of this model here, okay, if we arrive at this and if we argue that it's, we can instantiate some analysis, okay, so to implement it, we can use some generic mechanism or generic programming mechanism, right? But the question is, what if we start from only, what is the generative power of this approach? Can we start only from this and generate the rest? I mean, within a specific, within some domain, right? So this is a question. Again, I think, yeah, so at least in the product line community, we haven't seen many approaches in these directions yet. Other properties of interest, so can we instantiate and perform this analysis to different properties? In terms of the mechanization, at least from our side, we were more migrating these days more to another proof assistance, so the cross proof assistance. We originally started just for social reasons, so to say, with PVS, because there was more experience in the team, initially in PVS, but then we started to move more to COS, basically because there's much more, the community is much bigger, there's much more resources in terms of cost. So we decided to also to move there, also because it has some code generation, very interesting code generation capabilities that we could explore to synthesize the system and have even more confidence that they are actually correct by construction, right? So this is also very important. Well, another topic here, I mean, it's also maybe now thinking a little bit in this small, in terms of application domains, we're talking about some a specific application scenario, right? In terms of, which is, I think it's relevant, this monitoring the body sensor network. I mean, started working on this actually from at least 10 years ago and more. But as we can imagine, this is still relevant, at least area of application. But there are, I mean, as we scale up to other scenarios, we want to consider also some command and control systems. Here, command and control is something very general these days. Not only it was born in the military domain, but these days something for very, very general. So, for instance, the pandemic scenario can be seen within a command and control perspective, right? A challenging one, of course. But the idea is that when we consider kind of a set of systems, right? So not kind of ecosystems of multi-agent systems, right? So there we want to do some command and control, and we want to do the same analysis again, right? But it's but that's very I mean, it's good, right? That's very interesting, but it's very even more challenging, right? Because we have a number of issues just analyzing application running a mobile phone, not to mention in these much larger systems, ecosystems, and so on. But it's very, very relevant. So we, I mean, just to give an example, in the group, there's a one PhD student that's working on this, actually just command control, but not exploring this kind of analysis here. It's very hard to do that. It's exploring some what we call agility in this domain. The agility is the capability of the system to adapt to changes and still keep doing reaching its goals. But this there's some formalization efforts there. We just started to at least provide some formal specification using channel systems, but the analysis there is much more complicated, right? But this will be naturally kind of future work. But this is there's plenty I think of opportunity here. Okay. So with that, I conclude the presentation. Thank you very much.
Thank you so much, Vander, for a very interesting talk. I'll open for for you to give questions or comments, and then we can discuss a bit more later. Well, let's see. Let's start with Vidas.
Thank you. My question is about product lines. What is the place of product lines now when we have highly decentralized systems like microservices, Lambda functions, and blockchains?
Okay, so product lines have been explored in different levels of abstractions, right? So originally started with more like just coding or very specific programming techniques, but the abstraction has risen from implementation artifacts to design to requirements to business process and so on to test also. And in a coarser granularity also for services, right? So I think the original work in this area date already for 15 years, right? The work by J. Jun Lee and colleagues from Lancaster, previously was from Harvard and Lancaster University. So they already addressed this. It's still a topic of investigation, at least for service oriented, but for microservices, I'm really not aware to how far that has been explored. Neither for blockchain. So I think there is for sure possibilities there.
Okay. Anyone else? Any other questions? Gustavo?
Hi, Vander. Thank you for the very interesting talk. I had two questions. You have already answered the first one. The first one was, I was going to ask you if you had any particular reasons for using PVS instead of other proof assistants. You have already answered this. So my question is, how is the porting from PVS to COC? Are you facing any interesting challenges?
Yeah, so that thanks, Gustavo, for the question. So their experience so far is that we can reuse more the design, the idea, but in the very detail, it's quite different, right? So in PVS there's grind, in COC we have other tactics. Sometimes the correspondence between the tactics is not very immediate. So we are leveraging more the structure of the proof rather than the specific comments, right? So reuse is limited here in the detail. That's our experience, and that's also that's frustrating a bit.
Okay, thank you.
Good. We have more time for questions. Let me ask one question, Vander, and then we can go to the other questions. You said that I would like to see what is the actual burden of the proof obligations you have for the theory you presented, because at first, if you look at the theory, it seems simple, but you know it's never simple when you go to the proof obligations. So what is the actual what is the heaviest part that makes proof obligations hard to prove, or manually, for example?
Well, so then I have to refer you to the specific details in the repository. So from I mean, just like that, I cannot answer directly, but we can just say I can just recall the slide here with the numbers. I can just say that the proof obligations represented about a third. The manual proof obligations represent a third of the effort, right? So Okay, there were some automatic ones, but on the other hand, no free lunch, you get quite a number of manual ones, right? So, but yeah, it's just, I mean, it's part of that, right? So for termination, for example, right? So a lot of, because the way, I mean, Coq solves that in a different way, right? So you have to have you work with total functions, so that's how Coq does that. But in PPS, then you have to prove that, right? So sometimes that takes quite some effort.
So you think with Coq this would be different?
Well, but then again, it's not trivial. Sometimes you have to encode this specification. Sometimes it's not very trivially done, right? So then there's more effort. Perhaps it's like you have specification and you have proof. We are always dancing between these two. So if we make the proof effort a bit more lower, then at some point we might have to increase the complexity of the specification. So yeah, so it's hard to say which is better. I mean, I would say at the moment, so just to recall that the two main reasons for migrating to Coq is that first, in terms of community, available resources, and also we want to train people, right? So I mean, the students, they go away, they stay for some time, they leave, and they're new students. It's important to be able to train efficiently for proof in terms of automatic verification. That's with pure improving. That's a hard effort, as we know. And the second is that we can also leverage the code generation capability of Coq, so that we want to explore that to have confidence that our code is actually what really we specified, right? And that we're not introducing noise in the implementation, right? Which of course we know can happen, but we just address that informally using tests and so on.
Great, thank you. So do we have any additional questions? Just want to close it. Just one final question. The first half of your presentation was about reliability, right? Especially for BSNs, which is the main application of the layered framework you presented. What is the current? Can you say something about the current state of practice in verifying BSN's reliability?
Okay, so well, it's still a big challenge, I should say, right? So what we see is more application in the, I mean, some different domains. Really, at the moment we see more like a high level, just specification, but not really verification of properties. So that's, I mean, that's at least as far as I know.
Okay, very interesting. So I guess we're finished. Thank you, Vander, again so much for being with us today and presenting your research program. I would say it's not only a research work, it's a research program, which is very interesting. It's several topics and parts that have been built along these years, and we have certainly several parts that will be topics for future work. So it's very interesting. We'll try to catch up as soon as you have new results. So thank you.
Thank you very much.
Thank you for being here, for the audience. Just a few notes. We'll be back today for the school session or tutorial on timed automata, which is does fit into the subsequent technical session, which will be centered on automata. So if you're doing the school, it's very interesting to hear the tutorial, to get here and participate, and then you will be much more prepared for the final the sessions, the technical papers, ask questions and participate. So we're going to publish probably today on the SBMF YouTube channel the videos from the keynotes and the tutorials or the lectures from yesterday as well. Will be published in the YouTube channel. I'll be sending you the link to the channel later on Discord. Okay, so you have any questions, feel free to contact me or any of the organizers. The staff will be here on Discord. So I'll see you later after lunch for the tutorial. Bye-bye. Thank you.